Hi everyone, welcome back. In this video, we will continue on oscillator theory. So what we are going to do now is we're going to start introducing concepts that will lead to the perturbative projection vector. Okay, so that's another model for oscillator theory, in oscillator theory, for oscillator phase noise and injection locking, things like that. So we'll start introducing those concepts in this video. Okay, let's get started. So I'll call this oscillator theory. And in this video, we will discuss what is known as the state transition matrix and Floquet theory, Floquet's theorem, or Floquet theorem. Okay, so I mean, we need these kind of prerequisites. These two concepts, the state transition matrix and the Floquet theorem, are necessary for us to understand the perturbative projection vector model, PPV model, that was developed by Alper Demir and J.G. Roy Choudhury. So okay, so what are the prerequisites? So this is actually quite a mathematically dense model. So there are some mathematical prerequisites that I will not cover in this video. I'm going to assume you have them. So what are they? So the first one is linear algebra. So in linear algebra, you should know what are eigenvalues and eigenvectors. Then you should know what is the notion of a linear transformation. Right? So what exactly is a linear transformation? And you should know the fact that a given matrix is a representation of a linear transformation in a given basis, right? So you should know obviously you should know what a basis is, what span is, and all these terminologies. And another thing which it would be good to know, but if you don't know, it's probably okay, is matrix decompositions, right? So this will help if you have intuition for what this is. So one of them is like the eigen decomposition and singular value decomposition. If you know what these are, that would be very helpful, right? To follow what's going on. And I would really recommend people to go watch 3 Brew, 1 Brown's series on linear algebra. And that'll give you a very strong intuition of what exactly eigenvalues, eigenvectors, and most importantly, you need to know what is a linear transformation, right? And how why a matrix is a representation of a linear transformation. If you know all of this, then you have at least this prerequisite sorted out. The next one is, of course, you should know what differential equations are and have some uh, level of expertise not expertise, but some level of knowledge, I would say. So you should be able to do like basic vector calculus in Rn, right? So it's not just R3 as usually done. You should be able to deal with calculus over vectors of any dimension. It is not a very strict prerequisite, but the linear algebra one is very important. Okay, one more note that I want to make is that we are not going to not discussing proofs of different theorems. So I'll state a theorem, give you the intuition behind the theorem, and in some simple cases, maybe I'll go through like quick proofs, right? This is not a math course, really. It's just building up the mathematical prerequisites for PPV model. So that's why I don't want to go into like too much detail. Okay. With that, we can get started. So the first thing we want to look at is, so just to get warmed up, linear homogeneous differential equations. Okay. All right. So a coupled set of differential equations, right? So I can write that as vector x dot is equal to matrix A of t and multiplied by vector x, right? So that's kind of the general representation of a homogeneous differential equation where the matrix A is time varying, right? Okay. So what's an example? Let's take an example for simplicity, right? So I can say, okay, the voltage and current of an LC oscillator. We actually looked at this in the video on the nonlinear model example of a LC oscillator. Can be written as some differential equation, right? In that case, it was actually a nonlinear inhomogeneous differential equation, but in this case, can be some function of time, some matrix function of time, times the voltage and current, right? So since we'll mostly be dealing with second order differential equations, this is kind of an example of a homogeneous case of that. Okay, so just to get warmed up, it's good to think about what exactly this is saying, right? So what is this saying? Intuition. I always like to focus on intuition. So what exactly is this saying? So this is saying given a vector x, some vector x, right? This gets multiplied by a matrix A and goes to some new vector x dot, right? X dot. But x dot is the derivative of x, right? So this is just saying that this vector x of t, if you want to know what is the evolution of x of t with time, all you need to do is multiply x of t with this matrix A or linear transform. It's a linear transformation, right? You transform x to its next time instant. So let me redo it. So I say, okay, this is x at t, and this is x at t plus delta of t, right? And then this is essentially x dot of t, right? The derivative of this vector x. So it's saying that if you want to find out how exactly x of t is changing, which is determined by its derivative, that is just given by a multiplied by x, right? So essentially, this is telling you how every single vector x in the space Rn is changing with respect to time. So this is essentially, so this equation, so this thing is describing how a vector x uh, changes with time, right? Or you could also say, instead of how a vector x changes with time, you could say how Rn itself changes with time, right? So some space Rn, which in 2 dimensions is just the xy space, for example, how that entire space, all the vectors on that space are changing, right? It's like warping, how that space is being warped. So with time. And of course, here a of t is a function of time. Even if a of t is not a function of time, that will describe how that space is changing with time, right? So this is like a time varying model. Time varying model. Okay. So I should actually have said this before, but here x belongs to Rn, and x of t naught is the initial condition, can be written as x naught. Okay. So if you have an idea of what linear transformations are, all of this should be fairly obvious already, but that's kind of what it is. So, okay. So there's a theorem which says that under sorry, certain sort of general conditions. So it's not something very important, the conditions itself. Conditions on A of t. It can be shown that the solutions of equation 1, which we should actually label, or we did label that, okay. Solutions of equation 1 span Rn. That's very important. So what does that mean? That means that given an equation like this, if I want to find out what are all the vectors x that satisfy this equation, right? So this x of t is some vector that changes with time, and you want to find all the vectors whose derivative is related to itself by this matrix A. All of those vectors actually span the entire space itself, Rn, right? And one way to think about this is to say that, okay, you could say equation 1 is, or not is, but can be interpreted as a generating function of some sort of a generating equation for x bar, right? So if you look at it this way, then it's obvious that actually all of the solutions to that equation should span Rn, because given any x, if you multiply it by a, it'll give you x dot, right? So obviously that x would satisfy that equation, and every x satisfies that equation in Rn. So of course the solutions to that equation should span all of Rn, right? Okay, so this is actually very important. It's might be not so obvious, but it is important that every solution of the homogeneous equation given above spans the entire space, right? So every vector actually satisfies that, if you think of it as a generating function. Okay, so let's ground ourselves up a little bit. Why do we actually care about this, right? So why do we care? We care because oscillators, as we saw in the previous videos, especially in the nonlinear model video, oscillators obey second order nonlinear differential equations, right? Which is something like x dot is equal to actually this is linear, so I won't write an equation for it, but we know that, okay, oscillators obey second order nonlinear differential equations. So it is important to study the dynamics of such systems, right? Such systems in the language of differential equations. Okay, so that's the reason why we're actually doing this, is to, if you really want to make a rigorous mathematical model for oscillators, we need to build a mathematical framework to do that, right? And that's kind of why we're here. Okay, so going back to this theorem, which says that under certain conditions A of t, on A of t, it can be shown that the solutions of equation 1 span Rn, right? Okay, so I can write, so I'll say let phi of t comma t naught comma x naught, where x naught is the initial condition at t naught, be the set of solutions of 1, equation 1. Okay, so essentially I'm saying that at a given point in time t, right, phi represents a vector in Rn that satisfies that equation, which is of course every vector, right? But the fact that this phi is not just a random vector, it's the vector, it's where the given vector x naught went when when you went from t to t naught, right? So at t naught, it was x naught, and at given time t, it's now phi, right? So this phi is actually a vector. Okay. So in this, at least in these notes, I'm following the notation that Alper Demir uses in his book and his papers. So just to be consistent. Okay. So obviously, again, since this is every vector in Rn, phi of t comma t naught comma x naught spans Rn, right? Spans Rn. So the set of all these vectors, as time progresses, since you started from every vector in Rn and you saw where those evolved from t naught to t, those would also be every vector in Rn, and that would obviously span Rn, right? Okay. Now, if I say if some xi, these are some initial vectors, is a basis for Rn, right? So we said that, okay, if xi is a basis for Rn, then where these xi go from t naught to t can be written as phi of t naught xi. And you can show that this is also a basis for Rn for all t. Right? So essentially, if you start with a basis and you see where these basis vectors have evolved with time, they'll always comprise a basis for Rn. Okay, that's what that statement is saying. And all of these are kind of intuitive if you understand basic linear algebra. I'm not proving any of them, that's why. And I can write these vectors as phi I of t, which is phi of t, comma t naught, comma xi, right? And that's why the subscript from uh, here went there, right? So if I start from some basis vectors xi, and I see how they evolve with time, given that equation 1, all these vectors still remain a basis for all time. That's what that's saying. Okay, so with that, we are ready to now define something called the fundamental matrix. Okay, so the fundamental matrix is nothing but x bar, double bar, I guess, is nothing but these phi i's written out as columns of this matrix, phi n of t. So all it's saying is that given some initial basis, if I track that basis over time, you can write that as they will always remain a basis. And this basis can be written out as a matrix where each basis vector is the column of the matrix. And that matrix gives you, it's called the fundamental matrix. Okay. Okay. And then finally, now we're ready to define the state transition matrix. Sorry, state transition matrix. Okay. So if psi I of t is equal to p of t, comma t naught, comma xi hat, then x bar is the state transition matrix. That's it. So what I'm saying here is that here we said, okay, you start from some basis and then you track that basis over time. And then that the vectors you get are essentially columns of the fundamental matrix, right? But instead of some random basis, if you start with the canonical basis, right? So let me actually define that. Where xi hat is the canonical basis, right? 1, comma 0, comma, and this is in the ith position. So this is like the x hat, y hat, z hat in R3, right? So it's the, yeah, x-axis, y-axis, z-axis, I guess. So these are the canonical basis vectors. And they're called the canonical basis vectors. Okay. So what this is saying is that you basically have some system which is evolving with time, whose evolution is determined by equation 1. If you look at the canonical basis vectors and you say those are the start initial conditions, and you see how these vectors have evolved with time, they give you some new basis vectors, right? And those basis vectors, when you make them into columns of a given matrix, that matrix is called the state transition matrix. So in other words, okay, so it is the matrix whose columns have evolved from the canonical basis vectors. Because as t went to t naught went to t, right? From t naught to t. Okay, so why is this useful, right? Um, so I usually, or at least um, it's written as, this matrix is written as phi of t comma t naught comma x1 hat. So where did the first vector go? The second column is phi of t comma t naught comma x2 hat, and so on, right? Okay, so why is this useful? So if you understand linear transformations, you'll understand that essentially any transformation can be represented by a matrix, and that matrix representation of a linear transformation essentially is telling you, the first column of the matrix tells you where the x-axis went. The second column of the matrix tells you where the y-axis went, and so on, right? So a matrix is a representation of a linear transformation in the canonical basis, in any way, in some basis, and generally uh, for a given linear transformation, in the canonical basis gives you the matrix representation of that linear transformation, right? So that's what this is saying. So this is essentially the state transition matrix tells you how it essentially captures the full dynamics of your system as time progresses, right? So I would say it is the fundamental characterization of equation 1, right? Of I should say actually not equation 1, I should say of how equation 1 warps with time. Warps Rn with time. Right? So essentially it's saying, okay, I'm looking at where all these canonical basis vectors are going with time. And that's what the state transition matrix gives you. And if you know where the canonical basis vectors are going with time, then you know where exactly every vector is going with time, right? And that's why it's the fundamental characterization of a given homogeneous differential equation. Okay, so what I just said is that, therefore, to know where an arbitrary vector x naught, let's say, went from t naught to t, all you have to do is multiply, simply do phi of t comma t naught comma x naught, right? So where x naught went with time, which we said was phi, can simply be given by the multiplication of that vector with the state transition matrix. That's it. right? So it's very nice. So if you have the state transition matrix for a given linear differential, homogeneous linear differential equation, then you've essentially solved the problem, right? So then you know, okay, if I want to find a given vector where a given vector went, you just multiply it. That's it. Okay, that's why it's so powerful. Uh, so far, we haven't actually said how to compute the state transition matrix given a system. We've only said that it exists, right? Based on the theory, at least. Okay, so now we'll move on to linear inhomogeneous differential equations. Okay, so that looks something like this. X dot of t is equal to some a t, x of t plus b of t, right? And of course, x of t naught is just x naught. Okay, and I'm not going to prove it, but there's a theorem which says that the solution given the state transition matrix of the homogeneous case, right? So let's say I know what the state transition matrix of this, then the solution is given by t comma t naught comma x naught is the state transition matrix and x naught plus an integral from t naught to t of the state transition matrix beta. Right, so that's maybe somewhat straightforward. So you essentially have said that for this part, you get the homogeneous solution. And for this part, you need to integrate where the state transition matrix took it at each point in time, because at each point in time, it's an addition, right? So you have to add up all of those things, and that's where this integral comes from. That's kind of the very high level hand wavy intuitive explanation as to why the solution is given that way. But you can prove it, of course, which I'm not going to do. Okay, and as I said, we don't know how to calculate this. We just know that it exists, right? Okay, and now we're ready to move on to the case that we really care about, which is going back again to linear differential equations with periodic coefficients, right? So we are dealing with oscillators, so we care about systems where systems that are periodic, right? So where a of t is periodic. So this can be written as, this is again the homogeneous case, x dot is equal to a double bar of t times x of t, where x of t naught is equal to x bar, and a double bar of t plus t is equal to a of t. Okay, so what this is saying is that I have some system, and the vector is evolving with time, of course. The system also can change with time, but the change of the system changes with time periodically, right? So like an oscillator. So if I'm looking at, let's say, the voltage of an oscillator, and the oscillator is in steady state condition, which means it's periodic, right? All the voltages, not all the system itself is periodic. And we're looking at solutions to such a system. Okay. All right, so let's make some quick observations. Is x of t periodic? Right, so I said, okay, the system is periodic, but does it mean that x of t has to be periodic? And the answer to that is no. In general, x of t does not have to be periodic. It may be, of course, but it doesn't have to be. So a simple example to illustrate that is if a of t is some kind of a scaling, right? So for example, a of t is scaling by, let's say, 2 in every period, right? So within every period, it kind of scales every vector by a factor of 2. So of course that can be periodic. So every period it scales by a factor of 2 and so on and so forth. But of course, the vectors keep getting larger and larger, and the solution of X is not necessarily periodic, right? So the system is periodic, but the solutions in X are not periodic, right? So that's one observation. That's pretty straightforward. Okay, the second one uh, is phi of t periodic. So let's say you start from some t naught and you end up at t, state transition matrix. Is that equal to phi of t comma t naught? Again, the answer is no in general, right? And why is that? I mean, obviously, if x of t is not periodic, then you can clearly see that phi of t would also not be periodic, right? Need not be periodic, because phi of t is just a combination of different x's for different times, the basis vectors, right? So then the question becomes, what can we really say about the periodic properties of phi? What can we say about the periodic properties of phi? We care about this because phi, this phi matrix, the state transition matrix, kind of, we saw that that's what determines the solutions, right? So if you know that, you know pretty much everything. So essentially what we want to say is that, okay, we have a periodic system. So phi should have some kind of periodic structure to it. It cannot be totally aperiodic. So it has to be some kind of periodic structure to it, which is what your intuition says. So what exactly is that periodic structure, right? That's what we want to know. And that is given by Floquet's theorem. Okay, so it's a big theorem, so I want to put it in a new page. Okay, so it says that this phi, and now I'm going to use S and T, but you can also say T and T naught, it doesn't matter. Let's use T and S, T comma S, right? So this is the matrix that takes the canonical basis to a new basis at time t. And Floquet's theorem says that this can be written as a product matrix decomposition of three different matrices, U of t, D of t minus S times V of t, or V of S. This requires a red box. And each of these matrices, U, D, and V, have their own periodic properties. So I'll call this equation 2. And there's a lot of structure to this. So let's see what the structure is. So where U of t and V of S are t periodic. So phi itself is not t periodic because we'll see actually that D is not t periodic. D is sort of a complex exponential or exponential, diagonal exponential matrix. But U and V are periodic. And beyond this, they satisfy following relation: U of t is equal to V inverse of t, and vice versa as well. So V of t can also be written as U inverse of t. And D of t minus S is given by, it's a diagonal matrix where the diagonal entries are exponentials of the following form: mu1 t minus S, comma, dot, 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 exponential of mu n of t minus S. Okay, so you have a diagonal matrix in the middle, and then you have a matrix on the left and right, and they are inverses of each other, right? So it's very similar to, like, looks very similar to like an SVD, right? But it's not an SVD. Yeah. So it's it's saying that, okay, there is some basis given by this U matrix in which the state transition matrix can be written as a diagonal matrix, right? That's kind of what it's saying. Anyways, so this phi and d are essentially similar matrices. And to go from one to the other, you have to kind of do a basis transformation, which is given by these U and V matrices. And we'll see actually that these matrices play a huge role. You can think of it as just one matrix because they're inverses of each other, right? So this U matrix plays a big, big role. And the PPV essentially arises from there. Okay, so it's not done yet, I guess, the theorem, where these mu i's are called Floquet or characteristic exponents, and lambda I equal to exponential of mu I t, where t is the period, are called Floquet or characteristic multipliers. That's just the name, I guess. Okay. Multipliers. Okay. And this you can also expand. So expanding equation 2, since it's a diagonal matrix in the middle, you can actually expand it. So expanding equation 2, I can write it as phi of t comma s is equal to summation I equal to 1 to n exponential of mu I t minus s times ui of t vi transpose of s. Okay, this is also a very important equation which we'll use a lot. Equation 3. Okay, so again, where ui of t are columns of u and vi transpose of s are rows of v. Okay, and the last relationship, which can also be shown from the fact that u is equal to v inverse, you can show that ui and vi each span Rn. So they're also a basis for Rn. Yeah. And they need not be a basis. So span and basis are not exactly the same thing. So they span Rn and satisfy what are known as the bi-orthogonality relations. Vi transpose uj of t is equal to delta ij. The delta function is the Kronecker delta function here. So this is known as the bi-orthogonality relation. This also we'll use a lot, so this is also very important. So I'll call this equation 4. Okay, so that's saying a lot. Essentially, we've said that, okay, if I have a periodic system, which can be represented by, in this case, a linear differential equation with periodic coefficients, then the solutions need not be periodic. The state transition matrix need not be periodic, but the state transition matrix can be decomposed into a product of 3 matrices, which look awfully similar to SVD, but they're essentially a matrix decomposition where U and V are inverses of each other and they are T periodic, and D is a diagonal matrix given by these Floquet multipliers, right, or Floquet exponents. So this kind of gives you an idea of what's going on. I mean, if you take, for example, the scaling case that I told you about, In the scaling case, you would see that these diagonal exponents would all have a constant value. And each time, although u and v are not periodic, each time those vectors would get larger and larger, right? So that's the idea. Okay, and then we also expanded it out into the summation, and we saw that the columns of u and v matrices satisfy this bi-orthogonality relation. So with that, I would like to stop. I mean, essentially, we've just developed some mathematical preliminaries before we start discussing PPV theory. And hopefully this is a nice warm-up and a refresher for linear algebra and some differential equations stuff from earlier. And if you haven't seen that, that's fine. Hopefully this serves as a good foundation. So next video, we'll look at PPV theory and see what the perturbative projection vector is and how we can apply these concepts to the study of oscillators. Okay, thank you. See you in the next one.